Let me remind you what I was trying to do last time. We were proving a theorem by Besikovic, which says the following. You pick m equal to 2 and alpha in between 0 and 1, and consider the following set. J of alpha, which was the set of points in 0, 1, for which the frequency of the digit 0 was equal to alpha, and the frequency of the digit 1 was equal to 1 minus alpha. So the claim was that the Hausdorff dimension of this set was the following number: alpha log alpha, 1 minus alpha log 1 minus alpha, and all this divided by log 2. So the way we started proving this we started considering the following set, the following number actually. The entropy of the ergodic measures such that they support that set. Let me stress once again that if this measure is ergodic and it supports this set, then it is a consequence of Birkhoff theorem, because T0 of x is this, that if the measure is supported in this set here, this is equal to alpha, and this is equal to 0, 1/2, and this is alpha. And the same thing is true for the other interval with the same argument. Okay? So the strategy we proposed in order to compute this number was to consider the following potential. It was defined to be log of alpha if x was in the first cylinder, and log of 1 minus alpha if x was in the other cylinder. So what we did last time was to compute the pressure function of that potential there. We studied this real function, and we actually explicitly computed it, that it looks like this. Here passing through log 2, and here passing through 1. Yeah? Huh? It's not? Well, it doesn't matter. It's a symbolic thing. I mean, well, you can put it like this. I don't mind. I mean, there's no... What I do really care here is remove all the points in 1/2 and all the pre-images, which are like the points that you don't like because they might have a double representation in the base 2 expansion. But that set is very small. It doesn't carry any entropy. So for the purpose of this and all thermodynamic formalism, is a net, I don't know how to say, it's a small set, a set that doesn't carry anything. 0 Hausdorff dimension, 0 entropy, it's countable. You can forget about it. But if you prefer, you can define it like this, and we don't define it in 1/2. Don't mind. Anyway, it's like this, and we actually proved that there exists an equilibrium state. Actually, the Bernoulli measure, is an equilibrium state for the potential phi alpha. So in particular, 0, which is the pressure of phi alpha, was h mu plus the integral of this. And this line, t times h mu plus t times this, was actually tangent to the graph of the pressure. If you see the definition of our potential and the property that any of the measures supported on that set have, you have the following. If an ergodic measure is supported on that set, it has this property, then the integral of this function will be mu ergodic mu j alpha equal to 1, the integral of this potential with respect to this measure is alpha log alpha plus 1 minus alpha log 1 minus alpha. Okay? It's constant in this set, and the measure of this set is alpha. It's constant in this set, and the measure of this set here is 1 minus alpha. Okay? Okay. Pick any other measure here, which is ergodic, and supports that set, and consider the line h nu plus t times phi d nu. They have the same slope, they are parallel. Here you can see the entropy of this line, and here you can see the entropy of this other one. I draw it below. And the reason why I can draw it below is that because of the variational principle, if I stand here, I know that the pressure is the supremum of every measure that's like that. Okay? So if I'm considering measures that are supported here, they all have the same slope, and they cannot have more entropy because in that case, they will be passing through here, which means that the pressure will be larger than this value here. Okay? So what I've done, basically, is to find a measure for which this expression is maximized, which is actually the Bernoulli measure in here. I can easily compute the entropy of this measure, which is nothing but minus this number here. I know that the pressure is 0, so it's not that hard. So, okay, we found that number. And that's what we did yesterday. We found a measure that maximizes that supremum. Of course, that's not enough to conclude that the Hausdorff dimension of the set is what we actually claimed. In order to prove that, we're going to consider the following. Pick any x in J alpha, and let's compute the pointwise dimension of this point with respect to this Bernoulli measure, with respect to the equilibrium state for the potential phi alpha. Catherine defined this, and we have this kind of, if you want, non-dynamical formula. But she showed that in this context, the situation is actually much better. You can change this expression with a ball that probably has nothing to do with the dynamics with, let's start in 1, the cylinder of length n that contains the point, divided by the length of that cylinder. Okay? So I'm going to compute this. I hope that everybody understands what do I mean by the cylinder that contains that point, but I mean, you have the interval here, and the dynamics induced a partition of this. This is the cylinder, if you like, Z0 and Z1. If you're in here, your base M expansion starts with 0. If you're in here, it starts with 1. But then you can divide this in half again. So if you are here, the first two digits are 0. Here is 0, 1. Here 1, 0, 1, 1, and so on. So basically what you're fixing is more and more coordinates in the base M expansion. So another way of saying it, all the points that belong here are such that their first n coordinates are exactly the same. Okay? So after this small picture or remark, if you want, we can immediately note that this length is 2 minus n. Okay? In the first case, you're 1/2, second 1/4, and so on. So we can actually write the pointwise dimension now as follows. It's the log of the measure of the cylinder minus n log 2. So I will remove the 1 log 2 here out. And we have this. And this is actually the definition of entropy I gave. So we know that this is almost everywhere 2 minus alpha log alpha plus 1 minus alpha log 1 minus alpha. But that's not good enough for me in order to conclude that actually the house of dimension of this set is equal to what I've claimed. What I need, according to what Catherine has told us already, is that every single point, for every single point in that set, the pointwise dimension has to be exactly equal to the number of the theorem in basic coverage. Basically, I have to prove that this here is exactly alpha log alpha plus 1 minus alpha log 1 minus alpha. Okay? So let's try to compute this. We have to, of course, make use of the fact that we are in a set where the frequency of the digits is determined. It's not any random point that you pick. So what is this? The measure is Bernoulli. So this is alpha, and here I will need a bit more of space. So just that you see, the measure of here is alpha. This is 1 minus alpha. This is alpha squared. This is alpha 1 minus alpha. This is 1 minus alpha alpha, 1 minus alpha squared. Okay? So what I have to compute is how many times in this expansion here, j's in between 1 and n are such that aj is equal to 0 times the number of times that aj is actually equal to 1. 1 minus alpha, thank you, otherwise. Exactly. So let's apply log, and let's try to compute this number here. If you apply log here, you have finally that the pointwise dimension is minus 1 over log 2, the limit of okay, the cardinality, well, I'll do everything, j in between 1 and such that aj is equal to 0 log, it's okay, log alpha plus the cardinality of j's between 1 and n, so that aj is equal to 1 log 1 minus alpha divided by n. But this divided by n is the frequency at which 0 appears. And we're in a set, J alpha, where that frequency is actually fixed. It's the same for every single point in that set. Therefore, this is the frequency of being in 0, which is alpha. Log alpha, the frequency being in the frequency of 1, which is 1 minus alpha log 1 minus alpha. And this is great because what we have shown, we constructed a measure seated in that set such that for every single point in that set, the pointwise dimension is exactly equal to this. These two ingredients allows us to conclude that the Hausdorff dimension of the set that we were considering is actually this. And this is the proof then of the Besicovitch theorem. Okay? Great. Of course, one can think, well, you pick 2 digits, pick m digits, and see what happens. And of course, that has been done. And the proof I've sketched here works exactly. It needs only the obvious modifications. If you want to prove the following theorem by Eggleston, which says the following: pick any base and pick a bunch of numbers in between 0 and 1 with I in between 0 and m minus 1, then the Hausdorff dimension of the set of points for which the frequency of the digit I is equal to, sorry, this have to sum 1. For which this happens, then this is equal to what it should be log m. Okay? Same proof goes through. There is an extra minus, you're right. Hausdorff dimension is positive. Okay, so you fix a potential, which is the one that it has to be. You find the equilibrium state, which will be able to repeat the exact same computation that I did here. I'm not going to pursue much these kind of problems, but let me just say that one can start playing now, and one can easily state very difficult questions. For example, well, I don't know if they're real difficult, just let's not know. You can play around with the frequencies. Pick, for example, any m. So this is a question. And consider the set of points, I don't know, whatever you like, for which their expansion in base m is such that the frequency of 0 is, I don't know, 2 times the frequency of 1 and 3 times the frequency of 2. Compute the Hausdorff dimension of that. That example is actually possible to do it, but you can ask even harder questions. Whatever you like. I mean, put any function you are interested in and try to compute the Hausdorff dimension of the set of points that satisfies this kind of relations. That's really hard. Well, I don't know if that's that hard, but the techniques that we have doesn't allow us to prove it in a straightforward way at all. Okay? What I've sketched today actually allows you to deal with these kind of problems, the linear relations, in certain cases. If there are a finite number of points that do satisfy that.
No, there are finite collection of vectors that make this set union.
Okay, yeah, I know what you mean. If m was actually 3 in that case, for example. You pick all the vectors for which this relation is true, and you make the union of that. Well, one of the main problems you have there is that, as you know, the uncountable union of sets is not the supremum of the set. Pick the interval, any point in the interval has Hausdorff dimension 0, the union of all those points has Hausdorff dimension 1. What will happen in that case is that you will decompose this set in an uncountable union of points. But it is still true that there is one set, which is the one that, given this restriction, distribute the mass as even as possible, given this constraint, that maximizes that Hausdorff dimension, and it actually attains it. So the maximum of over all the vectors that satisfy that condition is actually the Hausdorff dimension of that set corresponds to the Hausdorff dimension of this one. So you can do it, even though there is the difficulty of that uncountable union of sets.
You mean that if you consider the surface or whatever that you consider?
Yes, the maximum is
The point that is realized the minimum distance to the vector with all geometries is going to be
the Hausdorff dimension. Yeah. But that's not always true, I mean, of course. If you add M4, for example, and you have no condition for the frequency of the other digit, then you're in big trouble, because then it can be 1, the Hausdorff dimension. It's not easy, but well, you can ask lots of questions like this, and well, if somebody wants to do it, go ahead. It would be nice to have results in that direction. Okay, I'm going to change of map now. In the first case, yes. The second one, no. No. There are some very specific quadratic equations for which you can actually compute by hand certain things, and you can do it. But say that I put a 7 here. Okay, nothing is known. It's very hard. Well, I don't know if that's hard, but I don't know how to do it. Okay. I'm going to change to another map, a map that has been mentioned now a few times, and actually properties of it have been discussed. I'm going to change to the Gauss map and try to prove a couple of things there in the same spirit of this type of results. So continued fractions. So every number in 0, 1 can be written in the following way. Where every point is an integer. The representation is essentially unique. It is unique for irrational numbers, and for rational you have to make a condition on the last digit just to avoid double identifications. But it's essentially unique. It has lots of very good properties, as you all know. For example, if a number is irrational, then the continued fraction expansion is infinite, whereas if it's a rational number, then the continued fraction expansion is finite. But not only that, it also gives us the best possible rational approximations of a number. As you probably all know, but I will say it anyway. So if x is irrational, then you can write x as an infinite expansion, and you can denote Pn Qn to be the truncation at the nth digit of this. That gives you a rational number that satisfies this. But not only that, it is a very good rational approximation in the sense that if you pick any other rational map, any other rational number for which the denominator is more or equal than Qn, then this approximation is better than the other one. Okay? So it's a very interesting map from the point of view of number theory and gives us lots of information. And as in the case of base M expansions, you have a dynamical system that is closely related to the continued fraction expansion, the so-called Gauss map. Which I think that Ombre already defined and Anton also used. It's a map defined from 0, 1 to 0, 1. X goes to 1 minus x, 1 minus x. You can picture it, and it looked like this. One half, 1/3, 1/4, 1 over n, and so on. That's the partition that 1 over x induces. And the map looks like this. My picture was not great, but well, with infinitely many branches. That's an important feature. And the relation with continued fraction expansion is again the same as the one that we discussed in the case of the base M expansion. Meaning that if you know the orbit, the whole orbit through the Gauss map, then we know all the digits in the expansion. And the reason, the argument is exactly the same. I mean, if a point lies in one of the intervals of the partition, say here, you know that the first digit in the continued fraction expansion is 2. If it lies here, it's 3. If it lies here, it's 1. If you iterate it, and they iterate lies here, then you know that the second digit in the continued fraction expansion is actually 1, and so on. So basically, if you go and look where does this point lies, that will tell you which are the digits that you have to consider. Okay? So basically, what I'm saying essentially is that the Gauss map acts as the shift in the continued fraction expansion. Okay? So great. As we know already, this map has an absolutely continuous invariant measure, the so-called Gauss measure. It doesn't preserve Lebesgue, as the previous examples. Is slightly more complicated. Note that the branches are not linear, so if you take an interval, then the sum of the lengths that you will get is not exactly what you originally started, but remark, the Gauss measure, which is defined for any Borel set like 1 over log 2 is invariant and ergodic. So if you want, again, you can conclude the same things that we already did. For example, this measure is absolutely continuous with respect to Lebesgue. So information that you obtain with respect to this measure will hold Lebesgue almost everywhere. That's the good feature of absolutely continuous invariant measures. You know that every digit appears infinitely often in Lebesgue almost everywhere, for Lebesgue almost every point. Okay? The same argument, Poincaré recurrence theorem. And then, using this measure, you can actually compute the frequency at which those digits appear, and remark, using Birkhoff, and this measure, basically what I mean is compute the measure of this interval using this measure. You have that the frequency of the digit k is Lebesgue almost everywhere. 1 over log 2 log k plus 1, no, k plus 2, k plus 1 square. Not sure. Something like that. Something that looks like this. You just have to compute the measure with respect to that measure of one of these intervals here. Okay? In this case, well, the frequency of the digits is not exactly the same, which is not surprising considering that the partition is not even as in the previous case. So great, you could also try to, in this context, try to repeat the same type of work we did in the case of the base M expansion, but that's certainly not as easy as what I did before. It's actually a very recent result of several people, okay? I don't remember, but it's not that easy. It's not that easy. But one can try. One can try. Maybe what one could try, and what actually will probably work, is to consider a linear version of that map. So to avoid all the bounded distortion issues that one has to deal with in this kind of cases, and you just consider a piecewise linear model of this. Take a linear branch here, a linear branch here, a linear branch here, using the same partition. Then it will be easy to compute the pressure function. I will do it maybe in a second. And you can actually make lots of computations. Still, even for that linearized version, obtaining the same kind of results that we discussed in the previous setting of the base M expansion is not at all easy. It's not trivial at all. And actually some surprising things happen. And that has to do with certain dynamical properties of the Gauss map. First of all, note that the space where this is defined is not compact. I'm not considering 0 here. Okay? There's no way I can extend this map somehow. I don't know how to name it at 0. And that causes problems. Also, this is a system that has infinite entropy. The way to see that this system has infinite entropy is to restrict it. Look at this. The entropy of T is infinity. How can you be convinced of this? Consider the restriction of the map to 1 over n plus 1 to 1. Okay? This is a map with finitely many branches, with n full branches. It's not hard to prove that the entropy of this is log of n. You add more branches, the entropy of a subsystem grows. In particular, the entropy of the full system is actually log n. Okay? That causes difficulties when you deal with the thermodynamic formalism, because in particular, at 0, if you pick any function, and you look at this here, for t equal to 0, this is infinite. Okay? T equal to 0, it's the entropy. The entropy is infinite. So if I pick a negative potential, this is decreasing. So it can do like this, or it can do, I don't know, it has a jump and do like this. I mean, there are several possible forms and shapes that the pressure function can take in this new setting that make things much more complicated. Tomorrow I will state a theorem regarding this kind of how using the thermodynamic formalism in this context you can prove actually some sort of number theoretical results. But I still have some time, right? 10 minutes? Okay. So I would like, before finishing, I'd like to ask a question somehow that will help you to understand the idea of Markov partition somehow. Okay? I like to stress that. And the question is, how do you compare, for example, we have seen already 2 ways of writing a number. You take the base M expansion of a number, and you take the continued fraction expansion of a number. What information you can get knowing one from the other? Normally very little, because they are essentially independent, but everything depends on how do you ask the question, of course. So in order to ask the question correctly, okay. So pick a point and define the following number. Kn of x is the number of partial quotients So partial quotients are the digits in the continued fraction expansion. Okay? I once said, I was giving a talk and I was talking about the digits in the continued fraction expansion, and somebody got very angry and told me, no, we don't have infinitely many fingers, so you should not call that digits. So well, I'm keeping partial quotients for that. And the number of partial quotients in the continued fraction expansion of x that you can determine from the first n digits in the base m expansion. So it's clear what I mean? You know the base m expansion. Take the first n digits of that expansion. So maybe you will be able to deduce which is the first digit in the continued fraction expansion. Okay, say, imagine here, and imagine that you have the partition on base m. Say that m is 1/3, m is 3, so we have 1/3 and 2/3. Okay? So if the first digit in the base m, base 3 expansion is 2, you know that the first digit in the continued fraction expansion will be 1. So the question is, how much information can you learn? Continued fraction. The digits in the continued fraction expansion. Well, okay. Let's use digit in order to avoid any. Okay, digits. Okay, yeah, that's better. Sure. So that's a question, and we actually have a very good answer for it. Well, we have a very good asymptotic answer for it. So what's the theorem? For every x in 0, 1, we have that this is exactly, the log goes up or down. It's exactly log m over lambda x, where lambda x is the Lyapunov exponent of x. This, of course, whenever the limits involved here, in this case, well, the limit exists. Okay? I'm sorry, T is the Gauss map, yes. Okay? So what this is telling you is that if you use, the more digits you use in the base m expansion, the more information you gain from the continued fraction expansion. What it also tells you, which is kind of interesting, but it's slightly harder to see, the Lyapunov exponent, what it measures is the exponential speed of approximation of a number by its rational approximations. So what it's telling you there is that you are fastly approximated by rational numbers, then you get less information. So x minus Pn Qn, this is more or less like this. Okay? So if this is a large number, meaning that this approximates this very fast, then the information, the rate of information we gain is very small. Okay? So the faster you approximate by rationals, the less information you get, and the more digits you use to code your number, the more information you gain. How do you prove this? It's actually not that hard. The only remark that you have to have in mind to try to prove this is that it's what I said before. A cylinder, for one Markov partition, say Tm, what it contains is the set of points which have the same first n entrances in its expansion. The same holds true for the Gauss map. Okay? You pick a cylinder for the Gauss map of length n. What you have here is the set of points which have the same expansion up to the first n digits. And what are these two numbers actually? This number is the rate at which the cylinders shrink for the Tm map. And this number here is the rate at which the cylinders shrink the cylinder that contains the point x. Okay? So basically what you're doing when proving a result like this is comparing the rate at which the Markov partitions decrease to a point. Okay? Has nothing to do with the number theoretical properties of the maps that I've considered here. But of course, it's nicer to state it this way. It is an interesting exercise. I mean, you can try. Okay, thank you. I'm so sorry. What? So X and Y.
Yeah, to multi-dimensional.
Ah, well, yeah, okay, yeah. X and Y. Sorry, and which map is the one that you consider? Jacobi-Perron, something like that. Well, that's a harder question because in simultaneous approximation, what happens is that the maps are not conformal. So the rate at which here everything shrinks is very easy to compute because there is only one dimension. It goes like this. But you have a rectangle, you have two directions. What happens in Jacobi-Perron, for instance, is that you have one expansion in one direction and another one in another. So what you're creating basically is rectangles. So it's not that easy to compare. I mean, you will have to estimate the size of the rectangle. And probably for that, you will need to use two Lyapunov exponents using the two directions. But I don't know if it's that easy to compare. In that case, how does one rectangle fits in within another? Because the type of phenomena that will happen is that if you have two-dimensional, say, continued fraction mass, Jacobi-Perron, and take another one which might be a skew product or whatever you like, what will happen is one of the Markov pieces can be like that, and the other one can go like that, you see? And that's the only common part that you have, so the information that you will gain will only be given by that intersection. Here it's easier, because you have only one direction. In the non-conformal setting, I have no clue how to do it, and I don't think it's that easy. But maybe, who knows?
Were you studying Diophantine approximation, there is a set of two well-approximable numbers, and then you have the set of which has full measure, and then you have the set of three well-approximable numbers that usually has measure 0, and there are some results about the Hausdorff dimension of these sets. And can they prove through thermodynamical formalism?
Well, you know, Jarnik's result, which is the one that I think that you're talking, says, well, I'm not going to say it. There's been lots of effort to try to prove Jarnik results from a dynamical point of view. I would say that one of the first attempts for that is a very nice and powerful paper by Sangiovellani, and my memory for names is bad today. Sangiovellani, at least, it's an IHEA's paper, where they defined the notion of shrinking targets. And they tried to do it, but did not succeed. But they built up a huge theory, which is very interesting anyway. But for that particular problem, they were not able to do it. And later on, Mariusz Urbanski also tried to prove that, but he was able to prove it for just some numbers and not all of them. And, well, that's all what I know. Maybe somebody has already proven it, but that's what I know. At least. I don't know. Maybe somebody has done it over the last few years. But it's hard. It's very hard. Because it's not that clear that dynamically defined. That's a problem.